Hey everybody. So today's Wednesday and you are almost halfway through the week already. Actually, you are halfway through the week. Hope your day's been going well. I think Miss Barabo passed back the homework and hopefully you guys got if you had any homework questions, you had a few minutes to be able to answer some of those. The anti-differentiation problems, I think in general that you'll see are not as bad as some of the things that you've been doing previously, curve sketching and optimization. The tricky part about antiderivatives, the thing to keep in mind is that you're always trying to guess what the answer is and then kind of check to make sure that it works. Okay, just to maybe I've got a few more things that I want to talk about antiderivatives today. We'll go through a couple of other examples. And then, again, we're going to do some preliminary stuff to prepare us for talking about a new topic on Thursday. Let's take an example. I'm just thinking about maybe another example kind of like the ones in the homework. Let's try to find the antiderivative of t squared minus sine t. And again, these bookend pieces are what tell us we're looking for antiderivative. An antiderivative, in case you want to remember, if I have a function and I differentiate it, I get a new function. If I anti-differentiate, I get the old function back. So anti-differentiation is supposed to be the reverse of differentiation. So what you're supposed to think about with these problems is, for example, what would I differentiate to give me t squared, and what would I differentiate to give me sine of t? Now, t squared is going to start with t cubed, but when I differentiate, that 3 is going to come down, so I'm going to need a 1/3 out front. So the first part of this answer, the antiderivative of t squared is going to be 1/3 t cubed. The other part that I get with sine is that sine is going to come from cosine, but again, the derivative of cosine is negative sine, so I need to start with a negative over here so that it all works out correctly. Now there's already a negative, so I'm going to have a minus cosine. So again, so that's going to give me a positive cosine. Again, think about if I put a cosine on here and differentiate it, I'm going to get negative sine. So that's going to work out correctly. And I got to put that plus c because the thing that we saw on Monday was that plus c is the most general antiderivative. Okay, kind of. We'll talk. There's an issue, and I want to talk about that today. But for the most part, that's the type of thing that we're looking at. Okay. All right. 4 things that I want to just briefly mention here on antiderivatives, and then we're going to set this topic aside, and again do something that's going to prepare us for another topic that we're going to see tomorrow. All right. The first thing that I want to do is I want to go back. There's one example we looked at. How do I anti-differentiate x to the n? And what we noticed was that x to the n has to start with one higher power, x to the n plus 1. So when I differentiate, I get x to the n. But that n plus 1 is going to come down front, and I don't want it there. So we have to put a 1 over n plus 1 that will eventually cancel that n plus 1 out that's going to come down. So the antiderivative of x to the n is x to the n plus 1 over n plus 1. Now that works great, except when n is negative 1. And if n is negative 1, then you're trying to divide by 0 here, and you're not allowed to do that. Okay? So when n is negative 1, in other words, when we're talking about x to the minus 1, in other words, 1 over x, It's a very special and different case. Now, you've already seen on the sheet that I've kind of given you a little bit of the answer for how this is going to work. 1 over x, if you think about it for a second, 1 over x comes from, if I ask what function when I differentiate it gives you 1 over x, the first thing that should come to your mind is natural log of x. Now that's close to the answer, but not quite the right answer, and here's why. The function 1 over x has a domain of everything except 0, right? There's values from negative infinity to 0, and there are values from 0 to infinity. If I said, what's the antiderivative of this? Should be a function that when I differentiate it gives me this part, and there should be a function that when I differentiate it gives me this part. The problem with using this answer right here, natural log of x, here's natural log of x, is that if I use natural log of x, the domain here is just 0 to infinity. It's not everything. So if we started with some negative part of this function, this answer is not going to give me an antiderivative for that. But there is a function that will give me an antiderivative. Okay? Let's back up for a second. And by backing up, I'm going to have to erase. Let's back up for a second. And one of the things that we thought about when we first did the natural log, when we talked about natural log of x, and how the derivative of natural log is 1 over x, one of the things that I mentioned was that the domain of natural log of x is 0 to infinity, and when we graphed what the derivative would look like, we noticed that it looked like this, and that actually was the part of the function of 1 over x. But one of the other things that we noticed was that if we took the function natural log of absolute value of x and differentiated that, we actually still got 1 over x. Let's look at that again just for a second, because I think this is going to be useful. The natural log of absolute value of x function, when x is positive, it's just the natural log function. But when x is negative, what that absolute value is doing is it's throwing on another negative sign to make this overall thing positive. Now what happens when I differentiate is that the first part, the derivative of natural log, when x is positive, is just 1 over x. But what I get on the second part is the derivative of this thing. I have to use the chain rule. I do derivative of the outer, plug in the inner, times the derivative of the inner. And what happens is those negatives cancel, and I get 1 over x in both cases, whether x is positive or whether x is negative. That means that this function right here differentiates to the function 1 over x, whether we're talking about positive numbers or negative numbers. What that means is that to go backwards, the 1 over x function anti-differentiates to this much more general natural log of absolute value of x function, which ends up looking like that. Okay? So the rule here is going to be that the antiderivative of 1 over x is going to be the natural log of the absolute value of x plus a constant. We want the most general antiderivative in this case. If we have a domain of positive and negative numbers, we need an antiderivative that also has a domain of positive and negative numbers. So whenever you do your antiderivatives of 1 over x and you're thinking natural log, always throw on an absolute value. Just remember to do that. Always throw on an absolute value. Okay? Just got to train yourself to do that. That's on the rule sheet there, but it's something to just remember. Okay? All right. Second thing that I want to just mention here, second note that I want to make, that concludes all of our rules for antiderivatives for now. So we're good there. Second thing that I want to note is that what we were saying before is that if the derivative of capital F is little f on an interval, then all antiderivatives of little f look like capital F plus C. That was a rule that I put up earlier. Okay, you don't have to throw that in your notes. That rule was there earlier. There's a key phrase that I have on here that's actually really important. It's on an interval. Okay. Here's what I mean by that. Let me give you an example here. Let's take the function 1 over x squared, and let's ask what its antiderivative is. Okay. So the way that we would need to rewrite that, just like you had to do on some of the homework problems, is x to the negative 2. And then I have to think, what function do I differentiate to give me x to the negative 2? Well, I would lower the power. So to go this way, I have to raise the power. So I need x to the negative 1. But if I start with x to the negative 1, I'm going to get negative x to the negative 2. I don't want that, so I'm going to put a negative on here, and that'll get rid of that negative that shows up here. So I would be tempted to say that the most general antiderivative is negative x to the negative 1, this one here, plus a constant. In other words, negative 1 over x plus a constant. Okay? The answer that I've written here is not wrong, but it's only correct on an interval where the function's defined. Okay, here's what I mean by that. Okay, on an interval, so you guys should probably remember what 1 over x looks like, right? 1 over x looks like this. Or maybe you do that backwards. Negative 1 over x looks like just the flipped version of that. So negative 1 over x looks like this. Okay, this is negative 1 over x. And that differentiates, we just said, to 1 over x squared. Okay, that was what we just figured out. Okay? Now watch, one of the things that we just mentioned is that if this is an antiderivative of this function, in other words, if I differentiate this, I get that. Then if I were to shift everything up by 2, in other words, if I were to look at negative 1 over x plus 2, if I were to take this entire thing and shift it up by 2, so in other words, now I have a horizontal asymptote of 2 instead of 0. Okay. If I've drawn this correctly, which I probably haven't, but that's okay, then the slope at x equals 1, the slope at x equals 1 is going to be the same because all I've done is I've taken this graph and shifted it up 2. So the slope, in other words, the derivative, is not affected by me shifting this entire graph up by 2. When I differentiate, I'm still going to get that function. Okay? With me so far? If I shift everything up by 2, if I add 2, that's not going to change the derivative. What if I were to subtract 3? That's not going to change the derivative either, right? But here's a question. What if I were to add 2 on one side and subtract 3 on the other side. So in other words, I took this graph and shifted the right side, or my left hand, the right side up by 2 and the left side down by 3. In other words, so I took this graph, and the right side I'm going to shift up by 2, and the left side I'm going to shift down by 3. So in other words, this function, let me call this capital F, looks like negative 1 over x plus 2 if x is bigger than 0. And then I subtract 3 if x is negative. What I want you to notice here is that if I'm taking discontinuous pieces, so this part is continuous. So if I take this continuous piece and this right here and shift it up 2, that is not going to affect the derivative anywhere on that piece. And if I take this piece and shift it down by 3, that's not going to affect the derivative there. So the derivative of this is also 1 over x squared. But you'll notice I was able to use different constants on the different continuous pieces, and that is not 1 over x plus a constant on the entire real line. This is not in this category. I'm using 2 different constants on the 2 different sides. So in other words, really, if you're looking for the most general antiderivative, anytime your function has a discontinuity, you're actually able to shift one of the pieces one constant and the other piece the other constant, and still able to get something that's an antiderivative of this original function. In this case, the most general antiderivative actually doesn't look like this. It looks like negative 1 over x plus 1 constant if x is positive, and negative 1 over x plus another constant if x is negative. Okay, so you can use 2 different constants on the 2 different continuous pieces. Now, when we actually ask for the general antiderivative using this notation, what we're talking about is on an interval where the function's defined. And on an interval where the function is completely defined, you're not going to get these discontinuities. Okay? If you're going across discontinuities, you can have different constants. So for instance, if we were talking about the function tangent, then with tangent, we could shift each piece a different constant, and the derivative is still all going to be the same. Does that make sense? So in general, when I give you this notation, if there's a discontinuity in the original function, then in the antiderivative, you can technically have more than one constant. However, when we use this notation, we're just talking about the function on one continuous interval. And in that case, you just write plus c. You don't have to use different constants on different intervals and that kind of thing. Okay? So that's a technicality that you just need to be aware of. All right. The third point that I wanted to make here, let's suppose that I have a function whose derivative, I'm going to write it like this, a function whose derivative is 6x squared. Okay, so the first thing I'm going to ask is what are the possible types of original functions that you could have had with this? So the thing that we want to think about is what function would I differentiate to get x squared? That's going to be x cubed. We'll leave the 6 alone. But if I differentiate x cubed, I'm going to get a 3 that's going to come down. So to prevent that, I'm going to put a 1/3 in there. Now to make this simpler, I'm just going to combine the 6 and the 1/3 and just make that x cubed. Now, I really should put a plus c because I could have a constant on there that could show up, right? And again, based on what I was just explaining over here, if this function actually had discontinuities, I could get different constants on the different continuous pieces. Here, this function's continuous, so I don't have any issues there. Okay, so the general function that differentiates to 6x squared is 2x cubed plus some constant. Now, what if I were to come along and give you some extra information and tell you not just that my function's derivative is 6x squared, but I were to also come along and were to say that the function that I'm talking about, when you plugged in 0, you get -1. This is sometimes called an initial condition. Don't worry about that terminology right now, but it's extra information that I'm giving you about my function. Now, what's going on here is that my function, it could be 2x cubed. Remember, x cubed looks like this, and so 2x cubed is just a scaled version of that. It could be 2x cubed, or it could be 2x cubed plus 1, or it could be 2x cubed plus 2, or it could be 2x cubed minus 1, or it could be 2x cubed plus pi. So there's this family of functions whose derivative all give me 6x squared. This part, this extra information, tells me which of these functions we're actually talking about. Okay, in order to nail down what the original function was, you need to not just have the derivative, you need extra information. This extra information would actually help me figure out what this constant is, because what it tells me is if I plug in 0, I'm supposed to get -1. But if I plug in 0, plugging in 0 for x gives me 2 times 0 is 0. I get my constant here. And so my constant is supposed to be -1. So the function that I actually want here, if at 0, I'm supposed to get -1, then the original function was 2x cubed minus 1. Does that make sense? Okay. Let's try one more example of that. Let's try, I have a function whose second derivative is 6x, and when you plug 0 in the original function you get 3, and when you plug 0 into the derivative you get 2. Okay? Let's try to figure out what my original function was. So starting from the second derivative being 6x, let's ask, what was the first derivative? Once we figure out what the first derivative is, then we can figure out what the original function was. So the first derivative, well, let's leave the 6 alone. The x had to come from x squared. But again, if I throw an x squared on there, that 2 is going to come down, so I need a half to get rid of the 2, so that I just get an x there. So the first derivative is going to be 3x squared. But I could have a constant on there, so I need to throw a plus c on here. So my first derivative could look like 3x squared plus some constant. Now I'm given some extra information about the first derivative here. I'm given the fact that when I plug in 0 in the first derivative, I get 2. So if I plug in 0, in other words, if I get 0 plus c, that's supposed to be 2. So that constant is actually 2. So the first derivative actually looks like 3x squared plus 2. Got it? So that's what's sitting here, 3x squared plus 2. So now let's look at the original function. Now 3x squared is kind of set up nicely. 3x squared is going to come from x cubed, so I don't even have to do anything there. 2 is going to come from 2x, right? If I differentiate 2x, that's what's going to give me 2. But I could have some other constant. I'm going to call that constant d. And it's this piece of information that's going to tell me what that constant d is. So if I plug in 0, in other words, I get 0 plus d, that should be 3. So d is going to end up being 3, and my original function is x cubed plus 2x plus 3. That is my function that satisfies these conditions, and then when I differentiate it twice, it's going to give me 6x. Make sense? So you'll have a couple of homework problems that are related to that as well. All right, the last thing that I want to say, number 4, the thing that I want to say about derivatives is, again, sort of emphasize, in general, differentiating is not that hard as long as you know the rule for how to deal with the function that you're talking about. We have rules for specific functions, so anything that looks like a sine we know how to deal with, or a secant, or an e to the x, or 2 to the x, or log base 5 of x. We have derivative rules for all those things. What we don't have is, in general, how to deal with antiderivatives. If antiderivatives have a very specific form, we can go backwards to get the function that differentiates to that. But in general, antiderivatives are very hard, and we're going to see that as we get into more of further on into chapter 4, and then later on in chapter 6 and 7. For the most part, what we're going to do at the beginning, you only need to know your rules backwards to be able to do them. So in other words, thinking backwards, you should be able to unravel most of the antiderivatives that we're working with. That it'll get more complicated as we go along, but for the most part, this is the level of complication we're going to have here. Okay, so why don't you take a 5-minute break, and then we will come back and talk a little bit about something called sigma notation. Some of you may have encountered sigma notation before, but if you haven't, we definitely need to go over it before we get into the next section. So take a 5-minute break, and we can come on back. Okay. So let's talk about sigma notation. Sigma notation is the thing that looks like this, or this. You should have seen these symbols before. You should probably also see them above the whiteboards. Okay, this is the Greek letter sigma. It's actually the capital sigma. Lowercase sigma looks like this, but we're not going to use lowercase sigma right now. But the capital or lowercase sigma in Greek stands for the Roman letter S, the English letter S, and S is the first letter in sum. So the sigma notation, this sigma typically means there's a sum going on of some kind. You've probably seen I think Miss Carricker has this sign on her door. I ate some pie. Some, right? So that's where that comes from. So I don't know if you guys have seen the use of this symbol before, but I'm going to kind of play it safe and assume that you haven't. So we're going to go through a little bit of how to read this sum, and then how to break it apart and how to bring things together in those sums, and then a few rules related to these sums. So first thing I want to go over, and I've got a summation rules handout that I've made here with some rules that we're going to go over. Don't worry about these right now, but let's go ahead and hand that out. And in general, the way you read a sum notation, okay, I'm going to do this in general, and then we'll we'll do this in some very specific cases so that this makes sense. But the way that you read this is the sum, so it's literally read, the sum, you start with the sigma notation, the sum from I equals 1 to n of, and then whatever is sitting there, of, in this case, a sub I. Okay, that's how you read this notation. The sum from I equals 1 to n, the sum I equals 1 to n of a sub I. Now, this is actually a compact form for a written out sum, and the written out sum begins with the first number, I, wherever you see an I in this portion, this is called the summand. Anywhere where you see I over here, you start with by putting a 1 in there and leaving everything else the way that it is. Okay? And then you increase by 1, so the next, after 1 comes 2, so what I would do is everywhere where I see an I, I'm now going to put a 2, but leave everything else the way that it is. Then I'm going to increase it again and go up to 3. And then you're going to keep going until you hit whatever this last number is. So if that last number is 10, you keep going until you hit 10. If it's 100, then you keep going until you hit 100. In this case, it's n, so I keep going until I hit n. Okay? So that's how you write out a sigma notation. This is how you read the sigma notation. Let's try a couple of examples here. Okay? Let's do the sum. I equals 1 to 6 of 2i. Okay? The way this works is it's going to be a sum, and I'm going to start with I equals 1, so I'm going to go into this formula, and everywhere where there's an I, I'm going to put a 1. So I'm going to do 2 times 1, and then it's a sum, so I need to put a plus. Then I'm going to increment that I up by 1, so now it's 2 times 2 instead of 2 times 1, plus, let's go up by 1, 2 times 3, plus 2 times 4, plus 2 times 5, plus 2 times 6. Okay, so this notation is a compact way of writing this long sum. If there's a pattern going on here, we can compact it into a nice short notation. Now I could compute what this is. I'm not going to take the time to do that. But that is the written out form of what's going on here. Okay? Let's try another example here. Let's try the sum I equals 3 to 7 of I squared. All right. So again, what I do is I take it's a sum, and I take the starting number as 3, and I plug it in wherever I see an I. So I'm going to start with 3 squared, which is going to be 9. Now it's a sum, so I write plus. Then I go from 3 to 4, so I'm going to write 4 squared. Again, wherever there's an I, I'm sticking that number in. Then I'm going to go plus, because it's a sum, then I go up again, 5 squared. 6 squared, and then plus 7 squared. So wherever there's an I start at this number and go up to this number, and I'm substituting that in with sums in between because there's a sigma there. Okay? Okay, let's try one more example. Let's suppose I had the sum j equals 2 to 5 of a over j. Okay? The sum j equals 2 to 5 of a over j. Okay, now I'm using j's instead of i's, but the number, the letter that you use doesn't matter as long as you're matching it together. So notice it's a sum, and I'm starting with j equals 2, so what I do is everywhere over here where I see a j, I'm going to put a 2, and everything else I leave alone. So notice I don't put a 2 in for the A. The A is just A. But the J starts at J equals 2. So I'm going to put A over 2 here. Then a plus. And now I'm going to increment J up by 1. So I'm going to do A over 3 now. Plus A over 4. Plus, and I'm going to stop at J equals 5. So A over 5. So this sum, written in a compact way, looks like this. So you can kind of see, if I have a sigma notation, how to write it out. Now the point is that if this was like 100, you would get really tired of writing all of this out. So we'd like a nice compact way to write this, and that's why the sigma notation was invented. So you've seen some examples of how to write out sigma notation. Let's see a few examples of how to write a long sum in sigma notation, okay? So let's suppose that I gave you the sum that's 1/2 plus a third plus a fourth plus a fifth, and I kept going all the way up to a 13th. Let's figure out how to write this in sigma notation, okay? So what I would need to do is, it's a sum, so I'm going to write sigma. And the pattern that I see is that everything is of the form 1 over something that's going up by 1. So let's give that something a name. Usually we use I or J. I'm going to use I, so 1 over I. And I, that number starts, the first time we see it, 1 over, in this case, we see 2 as the starting point. Then it goes up to 3, 4, 5, and it goes all the way up to 13. So this would be the sigma notation representing this long sum here. 1 over I, the sum, I equals 2 to 13 of 1 over I. Does that make sense? So this is a compact form for this long sum. Let's try another example here. Let's try C plus 2C plus 3C plus 4C all the way up to 10C. Okay? All right. So what we see, no pun intended here, is that this is first of all a sum, and everything looks like something times C. So let's write that as I times C, and I starts at 1 times C, 2 times C, 3 times C, 4 times C, and goes all the way up to 10 times C. Okay? Make sense? So this is the sigma notation for this. All right, let's do 2 more examples. 1 plus 4 plus 9 plus 16 all the way up to 100. Okay. First thing I want you to notice with this is that on the front end, this does not seem to go up by ones. 1 plus 4 plus 9 plus 16 all the way up to 100. However, there is something going up by ones. So you might notice that every single one of these is a square. 1 squared, 2 squared, 3 squared, 4 squared, all the way up to 10 squared. The thing I need to caution you about is that sigma notation only works if everything is going up by 1. If they're skipping or there's some random pattern, it doesn't work. Okay? So you have to get it in a form where it's clearly there's one thing going up by 1 each time. So in this case, what I see, it's a sum, and something is always being squared, so I'm going to write that as I squared. I starts at 1, and in this case goes up to 10. Okay, so that is the sigma notation for this sum here. Let's do one more example. Let's do 3 plus 6 plus 9 plus 12 all the way up to 27. Okay. Again, if this was 3 plus 4 plus 5 plus 6, then I would be fine, but it's not that. It starts at 3, and then I jump up to 6 and then to 9. But you might notice these are all multiples of 3. This is 3 times 1. This is 3 times 2. 9 is 3 times 3. 12 is 3 times 4. And then 27 is 3 times 9. So it looks like, sorry, my computer keeps going to sleep here. It looks like this in sigma notation, it's a sum. Everything is 3 times something, and that something starts at 1 and goes to 9. So this is going to be the sum, I equals 1 to 9 of 3i. Okay? Got it? Okay. Now, there's a few rules that involve sigma notation. I'm curious how many of you have actually encountered sigma notation before. Maybe you can raise your hand and Miss Verbo can tell me. You've probably encountered it at some point, maybe in algebra. If you haven't, that's fine. I'm not going to assume that you have, but it's helpful to know if you have seen sigma notation before. I want to tell you a brief story, and then I want to give you some formulas that will come from this story. No, it's not the unicorn story, Anna, but I haven't forgotten that. This story is about a young boy called Carl. His name was Carl Friedrich Gauss. Okay, Carl Friedrich Gauss. He's actually German. Gauss was actually, he went to school in a one-room schoolhouse with a number of other kids who were in all different grades. And the teacher of this school had a lot of problems managing the students, getting them to actually do what he wanted them to do. So a lot of times what he would do is he would throw busy work at some of them so he could work with other ones, or he would throw busy work at everybody so he could just sit at his desk and do some other things that he wanted. So one day, he decided to give all of the students this problem to keep them busy for a little while so that he could get some grading done. Okay? He said, I want you all to add up the numbers from 1 all the way up to 100. So I want you to take the number 1 plus the number 2 plus the number 3 plus the number 4 all the way up to 100. And what he expected people to do was go, well, 1 plus 2 is 3. And if I add that to 3, I get 6. And then if I add that to 4, I get 10. And if I add 5 more, I get 15. And 6 more is 21. And just sit there and kind of do that until they got to 100. What's interesting is about 5 seconds later, Carl Friedrich Gauss walked up to the teacher's desk and put down the answer. The answer turns out to be 5,050 to this. And the teacher was both flabbergasted and angry because the teacher now no longer has whatever time period, maybe 20 minutes that he thought he would have while these students practice their addition or something. He just instantly had answered it. Now you might be wondering, and Gauss was, I believe at the time he was 9. He may have been younger than that. So you might not expect that from an 8 or 9-year-old. 5 seconds, 10 seconds, something like that. Here's what Gauss did. He saw this sum and immediately he did the following, which maybe you might or might not do that. He imagined, let me write the last few numbers on here, 98, 99, 100. He imagined what would happen if we reversed the sum. Okay, so what if I reversed it and I had 100 plus 99 plus 98 plus 97, and it all went down to 3, 2, and 1. Okay? This sum and this sum are clearly the same sum. Those are two copies of the same thing. But what Gauss noticed was that if I added the two together downward, I get 101 in every single case. You see that each of these is going to add to 101. Okay, every single one of those is going to add to 101. So to figure out what this total is, I just need to know how many copies of 101 do I have. Well, how many copies of 101 do I have? I have 100 of them, right? Because they're kind of delineated right here. I have 1 through 100. I have 100 copies of this. So this thing is actually 101 times 100. In other words, 10,100. But 10,100 represents two copies of this thing. So this thing here is only going to be half of that. In other words, it's going to be 101 times 100 over 2. So if I take 10,100 divided by 2, I get 50, 50. And that was the answer he turned in. That was the answer he turned in, which made the teacher furious, but would make me super excited. So that's kind of a cool story, but here's the tie-in. This actually immediately leads to a really nice formula. If anybody ever asked you to add up the numbers from 1 to something, okay, so what you'll notice is that if we add up the numbers from 1 to 100, that turns out to be 100 times 101 over 2. Okay, so in general, the general formula that always works here is that if I were to take the numbers from 1 all the way up to some number n, okay, instead of 100, I'm going to use n, that turns out to always be n times n plus 1 over 2. Okay, so as an example, if I took the numbers 1, 2, 3, and 4 and added them up, that's supposed to be, according to this formula, 4 times 5 over 2. In other words, 20 over 2 is 10. And if you check that, it actually will work. Okay, if I take the numbers 1, 2, 3, 4, and 5 and add those up, I'm supposed to get 5 times 6 over 2. In other words, I'm supposed to get 30 over 2, which is 15. And if you check that, it works. So this formula actually works all the time. Okay. So, but if I were to put this formula in sigma notation, you'll actually notice it's the sum. Okay, this is the thing that keeps going up, so I'm going to call that I, and I starts at 1 and goes up to n. So anytime you see the sum of just I from 1 to something, it represents a sum like this, and this is what it actually adds up to. And you'll see that that's actually this third formula on your sheet here. Okay. Okay, so I want to go through just briefly, I want to take the last 5 minutes here and just go briefly through the formulas that are on your sheet there under the sigma notations, just so you can kind of see them. All right? So the first formula, you do not have to memorize these formulas. The first two are actually kind of intuitive once you understand what sigma notation is saying. The last 3, I will give you those if this shows up on a quiz. It's not going to show up on the quiz tomorrow. Okay, tomorrow is just Newton's method, differentials, and antiderivatives. Okay, but so the first what the first formula says is if I have a constant times something that has an I in it, let me actually write this out. So when I is 1, this would be C times A1. This next thing would be C times A sub 2, C times A sub 3, all the way up to C times A sub n, wherever this stops. If I have a constant here, notice I have a constant in all of these terms in my sum. Whenever we have a constant in common to everything in my sum, I can always pull it out. Okay, and if I pulled the C out, that would leave all of those other terms there without the C. Now, if I were to put that sum back into sigma notation, this is just A sub something, and that something starts at 1 and goes to n. Okay, so what this rule is saying is if you have a constant in your sum, in your sigma notation there, you can actually pull that constant out of the sigma notation. But it cannot depend on I. If there's an I in there, then you have to leave it in the sigma notation. If there's no I, you can just leave it alone. Okay, that's what that first step is just saying if you have a constant in there, like for instance, if you had the sum I equals 1 to 8 of 2I, you can actually pull that 2 out. And then if you can figure out what this is, so that's actually 1 plus 2 plus 3 all the way to 8, and we have a formula for that, then you can just take 2 times that, okay? That's actually 8 times 9 over 2. The 2's would cancel, and so you'd get, the answer would be 72. Make sense? So that first formula just means you can pull constants out of sigma notation, but just constants, not things that depend on the variable in the sigma notation. Second formula says if I have a sum of just constants, so let me actually write this out. So when I is 1, there's no I here, so I would just write C. Plus when I is 2, I just get C. When I is 3, I just get C. Okay, and then when I is n, I just get C. So I have a bunch of copies of C. The number of copies of C that I have is actually n copies. So that this sum just adds up to C times n. So if you're summing a constant, like if I were summing from 1 to 8 of 2, I would have when I equals 1, it's 2. When I is 2, it's 2. When I is 3, it's 2. Okay, this is always 2, and I have 8 copies of 2, because I went from 1 to 8. So this is just 2 times 8, which is 16. That's what this formula right here is telling you. That second formula on your sheet. If you're summing constants, just constants, then it's just how many times does the constant show up. Okay. That third formula on the sheet is already up here, so I'm just going to leave it. Okay, the fourth and fifth formulas on there also have other stories and other proofs related to them. I'm not going to prove them here. But the fourth formula says if instead of adding the numbers 1, 2, 3, all the way up to some number, you're adding the squares. So in other words, 1 squared plus 2 squared plus 3 squared, all the way up to some number squared. There's actually a formula for, it's called a closed formula for what that in total ends up adding up to. It ends up adding up to n times n plus 1 times 2n plus 1 all over 6. Okay, so for example, if I were to add the numbers 1 squared plus 2 squared plus 3 squared, we'll figure that out in a second. This formula would say, well, that will be n times n plus 1, it would be 4. 2n, n is 3, so 2n would be 6 plus 1 is 7. over 6. Okay, now I can cancel a 3 and I would get a 2 down bottom. I can cancel that with a 4. So according to this, that should add up to 14. If you add those together, that will actually end up giving you 14. Okay, so this is a way to add squares. This is a way to add regular numbers. And then finally, there's a formula for adding up cubes. So if I added up 1 cubed plus 2 cubed plus 3 cubed, all the way up to n cubed, that turns out to be n squared times n plus 1 squared all over 4. And you can think of some examples of that. There actually is a formula for sums of 4th powers, sums of 5th powers, sums of 6th powers. You might actually ask, is there a formula for sums of any powers? And the answer turns out to be yes. How to get it is kind of complicated, but there are formulas for all of those. You only need to understand intuitively pulling out constants and adding up constants. These 3 formulas, you may end up using them a fair amount, so you'll get used to them, but I will give those to you on a quiz if they show up. Okay? So be sure that you turn in your homework today, and you'll see a quiz tomorrow on Newton's method, differentials, and the first part of antiderivatives. Okay? I'll see you tomorrow.